Welcome to this session, Counting Principles 5, looking at combinations problems, this time with slightly more complicated restrictions, building on what we did in the previous video. So as a quick recap, in the last video we just looked at straightforward choosing of a group of students or items or numbers from a larger group. And we were not interested in the order or the arrangement of those. We were just interested in how many different ways I could choose the 2 or the 5 or the however many it was I was going to choose. So in this question, just to recap, how many ways could I choose 2 students to be class representatives from a class of 10 students? And that's just a nice straightforward combinations question. I've got 10 students to choose from. And I want to choose 2. So 10C2, 10 choose 2. How many ways could I choose 2 from 10? And if I just work that out in the calculator, it comes to 45. 45 ways I could choose those 2 students. No restrictions, any 2 will do. Notice that 10C2 is exactly the same result as 10C8. Because by choosing 2 students from a group of 10, I've also, at the same time, chosen a group of 8. Those 8 students are the students who aren't going to be class representatives. And that's the symmetry that we saw when we were looking at Pascal's triangle. Choosing 2 from 10 gives the same number of results as choosing 8 from 10 because it's symmetrical. Effectively, when I choose 2, I'm also choosing 8. Let's have a look then at where things get a little bit more complicated, although to be honest, not greatly complicated. So, same sort of setup, but this time my class of 10 students, there are 6 girls and 4 boys in the class. And this time I want to choose 1 boy and 1 girl to be class representatives. So I can think about the choosing of the boy and the girl separately. So the boy, I'm going to choose 1 boy from the 4. This is 4C1. How many ways could I choose 1 boy from 4? Well, hopefully you know the answer's 4 already. And then for the girls, I've got 6 girls. How many ways could I choose 1 girl? Well, 6C1, which hopefully you also know the answer is 6. Now, do I add them or write them down separately? Well, I must multiply. This is really important. It's always multiplicative because for every boy that I choose, they could be paired with any of the girls that I've chosen. So it's multiplicative. It's going to be 4 times 6, which is 24. So there are 24 ways that I could choose 1 boy and 1 girl to be the class rep. And again, that's not too complicated. Hopefully that makes sense. Let's take a step up in difficulty. This time I've got my class with 6 girls and 4 boys, and I'm going to pick a team of 4 students. How many ways can I pick the team if it must contain at least 1 girl? So this time, at least 1 girl, there's a number of different possibilities for the results. So I'm going to think about this problem in 2 possible ways, both of which will give the same result, and you can decide which one you like best. Often it'll be about which one takes least time, obviously. So if I've got to pick at least 1 girl, I could have a situation where I have 1 girl and 3 boys, or I could have 2 girls and 2 boys. I could have 3 girls and 1 boy, and I could have a team of 4 girls. So I've listed all the possibilities, and if I just work out how many combinations there are for each of those, then I will get a total. I can add them together and that will give me how many ways. So just very quickly, 1 girl I'm choosing from 6 is 6C1, and then I'm choosing 3 boys from the 4, that's 4C3, and so there's 24 ways that I could have a team of 1 girl and 3 boys. 2 girls, that's 6C2, I'm choosing 2 from 6, and 4C2, I'm choosing 2 from 4 boys. That will give me a result of 90. 3 girls and 1 boy, well, 6C3, choosing 3 girls from the 6, and 4C1, I'm choosing only 1 of the boys this time. This gives me a result of 80. And then lastly, 4 girls, 6C4, and, well, I could, for completeness, put 4C0, but the answer to that first item in Pascal's triangle is always 1. There's only one way I can pick none of the boys, and that's by not picking any of the boys, and that gives me 15. If I add those together, I get a total of 200 and 9. That works. It would just be not a very good method if it was picking a team of 27 students. I wouldn't really have to write down all the possibilities. So another way of thinking about it is that if there must be at least one girl, then that is the same as saying, well, all of the combinations apart from the ones where there's no girls. So if I worked out the total number of ways of picking the team and subtracted all the cases where there are no girls, that should give me the same result. Well, the total, no restrictions, 10 students picking 4. And if I subtracted the case where there's no girls, and to pick no girls, that's where I'm going to be picking 4 boys from the 4 boys that are available, and no girls, 6C0. And that gives me a result of 210 minus, well, funnily enough, 1. There's only one way that I can pick no girls, and that's by picking no girls. So I get 209. So that result there was a lot quicker to calculate than listing all the possibilities. But hey, it doesn't really matter. Whichever way you see it, both of them will give you the same result. Just make sure that in the options that you are calculating, you've covered every base, every eventuality, and you haven't missed anything. Here's a nice little question, looking at things slightly differently. Imagine we've got a restaurant, 3 tables, one with 6 chairs, the other with 4, and another with 5. And when a party of 15 people arrive, they want to know which table to sit at. The question is, how many ways could there be allocated to the 3 tables? And we're not interested here in which seat they're in, just which table they're going to go to. So the way of thinking about this is as a sequence of events. And the first thing we're going to do is we're going to take our party of 15 people and put the 6 people at the first table. So I've got to choose from the 15, 6 people to sit at that table, 15C6. Now when I've done that, I'm going to choose 4 to sit at the second table. So I'm going to choose 4. But I'm not going to choose them from the 15 because I've already sat people at the first table. So now I'm going to choose 4 people from the 9 who are remaining. So the first table, 15C6, 6 people are already accounted for. The second table, 9C4, I'm choosing 4 from the remaining 9. And then the final table, well, I'm choosing 5 from the remaining 5. I don't really need to do that last step because once I've seated people at the first 2 tables, I've already chosen the people for the last table, which gives 5C5 is equal to 1, so no surprises there. Anyway, if I work that out on my calculator, I get an answer of 630,630 ways. That's quite a lot of ways to seat people at these tables. Now, an interesting thing is, what if I did this in a different order? And maybe I'm going to seat people at the 4-seater table first. So this time I would have 15 people to choose from, and I'm just choosing 4 to put at the 4-seater table first. And then I'm going to put people at the 5-seater table. So I've got 5 people to seat, and now there are 11 left because I've sat the first 4. And then to finish, I'm going to seat the remaining 6 people at the 6-seater. Now here's the wonderful thing about the maths behind this, is if I work that out on my calculator, I get exactly the same result. So it doesn't matter which order I put people at the tables, I will get the same number of possible combinations for seating them. Order here is not important. One more example. Football squad, 3 goalkeepers, 8 defenders, 10 midfield players and 6 strikers. And I want to choose my team of 11, but the restriction here is there must be 1 goalkeeper, there have to be 4 defenders, 4 midfielders and 2 strikers, playing the good old 4-4-2 formation there for anybody who likes football. So again, rather like the restaurant tables, I can think about this as a sequence of events. So I'm first of all going to pick my goalkeeper. So I've got 3 to choose from, and I just want 1 goalkeeper. Then I'm going to choose the defender, from the 8 defenders available, I've got to choose 4. And then I'm going to choose from my 10 midfielders 4. And finally, from the 6 strikers in the squad, I'm going to pick 2. It's multiplicative because for any one goalkeeper that I choose, they could be paired up with any of those combinations of defenders, midfielders and strikers that emerge from this. So I have to multiply. And this gives me another huge result, 661,500 ways of picking a lineup for the football team. So you see how this works. Use of multiplication, thinking about the sequence of events, thinking about the easiest way to get to the answer, rather like the work we did on permutations. So why don't you have a go now? Practice question, pause the video and give this a try. 12 girls and 8 boys in a class. We want 4 students to do a presentation. How many ways can the group be chosen if A, there are no restrictions, B, there've got to be 2 girls and 2 boys in the group, C, there must be at least 1 boy and at least 1 girl in the group, and finally, there must be at least 2 girls in the group. Give that a try, pause the video, and I will go through that question in a second. So, there we go, 12 boys and 8 girls. Let's do the first one. No restrictions. That's a nice straightforward question. If there are no restrictions, we've got 20 students in total to choose from, and we're going to choose 4, 20C4, and that gives us a straightforward result of 4845. No restrictions there, nice and easy. There must be 2 girls and 2 boys, so this time I need to think about this as rather like before, sequence of events. I'm going to choose my 2 girls first and then my 2 boys. So I'm choosing the 2 girls from 12C2, and then multiplying that by 8C2, because I'm going to then choose my 2 boys from the 8 available, and that gives me a total result of 1,848. 2 girls and 2 boys exactly. Third question, there must be at least 1 boy and at least 1 girl. Now I could write down, like we did before, all the possible ways that have got at least 1 boy and at least 1 girl, but I think it's easier to think of this as total, all of the different combinations, minus all of those with 0 boys, because we can't have 0 boys, we must have at least 1 boy, and then also subtracting all the cases where there are 0 girls. Excuse my handwriting. So let's work out how that would be. 0 boys is me choosing the team of 4 from the 12 girls available. Could, just for completeness sake, say that I'm choosing 0 from 8. That gives me 495. 0 girls, how many ways could I choose 0 girls? Well, this time I'm choosing none from the 12 and 4 from the 8 boys, so that there are now no girls in the result, and there's only 70. So what I'm going to get here is my total, all the ways, no restrictions, 4845, subtract 0 boys, 495, oops, subtract 70, and that gives me a grand total of 4,280, where there are at least 1 boy and at least 1 girl. Note there, it was a lot easier to do that question by thinking about what we can find out really quickly, which is no boys and no girls. So last question, there must be at least 2 girls in the group. Well, in this case, it's probably quickest to just list the possibilities. To have at least 2 girls in the group, I could have 2 girls and 2 boys. I could have 3 girls and 1 boy, and I could have 4 girls and no boys. And then let's just work those out separately. For 2 girls and 2 boys is 12C2, because there's 12 girls, and 8C2 multiplied together gives a result of 1848. I think we did that in question 2, didn't we? 3 girls, 12C3 times 8C1, and this gives me a result of 1,760. And 4 girls and no boys, well, we did the no boys question just before, didn't we? 12C4 times 8C0, not choosing any boys there, 495. Add those together and I get a total result of 4,103 ways in which there's at least 2 girls in the group. So there you go. That is combinations with restrictions. I hope you found that useful. Practice, make up your own questions. Thank you for watching. Don't forget to like the video, subscribe to my YouTube channel, IB Maths Intense. Tell your friends I'm here, and of course drop me an email at ibmathsintense@gmail.com if there's anything that you'd like to see in particular, or if you've got any questions or any feedback or comments. In the meantime, enjoy your maths and take care.